Yeah, thank you for the introduction. I am Xihan Li from University College London. And I am a Google developers expert in artificial intelligence. Today, I'm glad to share some of the introduction about transformer models. Let me share my screen. Mm, Let me share. Okay, can you see my screen now?
Yes, it is visible.
Okay, yeah. So today I would like to share the mathematics behind the transformers, especially about word embeddings, positional embeddings, and attention mechanism. Yeah. And we know that transformer model is, we can say, maybe the most important artificial intelligence models in the world. Because it drives most of the mainstream large language models such as Gemini for Google, ChatGPT for OpenAI, or Cloud for Cloud, DeepSeek, GLM. So nearly all the large language models that you can name, is driven by transformers. Yeah. And today I would like to give a very intuitive introduction about how transformer models work. So generally speaking, transformer model work as predicting the next word, such as for example, we have a sentence, what is your name? And we would like a transformer model to give an answer. And the first step is that transformer model will process the whole sequence, and then it will try to predict what will be the next word that is proper as an answer to the sequence. For example, the first word it predicts might be I, and then the full sequence with the previous predicted word is treated as a whole and processed by transformer, and then it will try to predict the next word following the first word I, which could be maybe M. So it will recursively do this process again and again. For example, here we have Gemini, and then maybe predict next word. We have end of sequence. End of sequence means we need to stop. This is the end of the generation process. And then if we see an end of sequence token, and we will exit the iterative process. So here we have three questions to answer. That is, firstly, how do we represent a word that can be understood by transformer models? And the second is that, if we have multiple words as a sequence, like what is your name? We have 4 words. How can we represent the order of words so that the transformer would not understand the sequence like is your what name or some arbitrary order. So how can we represent the order of words? And the third is that how based on the word and order representation, how can we use transformer models to predict the next word that is most appropriate to answer the question. So before we answer the 3 questions, I would like to remind that there are 3 characteristics of a neural network. So neural network is a specific model that we need to take care of So what it is good at, what it is not good at. For example, if we have a neural network model, the transformer model is surely a neural network model. So we need to remember that such model is not good at internally differentiate similar values. For example, for a neural network, 0.999 and 1 is not very different. Yeah, as a parameter. Yeah, so that is why quantization works. Yeah, for nearly all neural models. Yeah, and the second point is that yeah, we almost always need to avoid large values to appear inside a neural model. Yeah, so we need to frequently do some sort of normalizations. Yeah, so something like this so we need to design mechanisms to avoid yeah a very large value within a neural network model. And the third part is that yeah the easiest transformation that neural network can learn is the linear transformation. So we try to make all the things we would like a neural network to learn as the linear transformations rather than other nonlinear transformations. Okay, so now we have 3 questions. Yeah, and we have characteristic of a neural network. And then we would like to show how we answer the 3 questions. So the first part is that how do we represent a word? Yeah, it seems like a very easy question because in computer we can surely represent a word. Yeah, so for example, we have text encoding like ASCII. Yeah, for example, for cat, CAT, we can represent it as three as a sequence of 3 letters, which is number 99, 97, 116. Yeah, something like this. Yeah, it seems very easy to represent a word in a digital world. Yeah. However, today we would like to let a transformer model, a neural network model, to process the word. The things becomes a bit different. So we would like a representation that is more standard, and more easy to be treated by neural networks. So in such a background, we can see that text encoding like cat, wolf, like this. Firstly, they have variable nerves. The nerves of a word can be different between words. For example, cat has 4 letters, wolf has 4 letters, 3 letters, 4 letters. They're not equal. This brings some sort of math, for a transformer model. Yeah, and also it is not that convenient to be treated mathematically because so the nerves of the variables can be changed. So we would like a simpler way, to represent a word. And then maybe you may say that, maybe we can simply, use an integer encoding. That is just to assign an integer to each of the word in a dictionary. Yeah, for example, maybe we have a dictionary of all the words, and we simply, assign a number like abandon 1, abbreviation 2, abide 3, like this. So each word we will assign an integer number. Yeah. It seems very convenient, but however, if we simply use integer, for our word, there would also be some problems. So we know that neural network is not good at differentiating very similar numerical values. Yeah. For example, if we represent zoom by 999, and we represent zoo by 1000. Yeah, it is pretty hard for a neural network to to find its difference because it is only the difference of them is only by one, which is very small. Consider their absolute value. Yeah. So if we use an integer encoding, yeah, a neural network model can easily mix up, yeah, zoom and zoo. Yeah. So we have to think of more ways to address this problem. Okay, so maybe we have one code. So next we have one hot encoding, yeah, which is in such a way, yeah, we do not assign a word with an integer. Rather, we assign a word with a vector. Yeah, the length of the vector is the number of words. For example, if we have 10,000 words, maybe the length of the length of the vector, yeah, will be 1,000. And here, consider that maybe if we only have 4 words, yeah, cat, dog, cow, and sheep, then the length of the vector would be 4. And for each vector, yeah, we set the index of the word to be 1 and other component to be 0. Yeah. So cat is 1 0 0 0, dog is 0 1 0 0. Yeah, something like this. Yeah. It seems that in such a way, we do not have the problems that we mentioned before because every word is equal. So, however, there's still a significant problem that you may already found, that is such a representation is too inefficient. If, for example, if we have 10,000 words, then the length of a vector would be 10,000, which could be too long to be processed by a neural network. And also, such representation does not represent any semantic relations between words. For example, we can never find the relation between cat and dogs or cow and sheep. Yeah, they are all very equal and isolated. Yeah. So to address the two problems, our final solution is the word embedding. So we have some sort of uh, algorithms that to build a semantic space and put each word into the semantic space to show their relations. And in such a way, not only the length of the vector can be smaller. Typically, it will be like around maybe 1,000 or between 1,000 and 2,000. Yeah, so it is much more efficient, and also it can represent semantic relations. Yeah, so you can see that cat and cat and dog, they are closer, and cow and sheep, they are closer because they are similar kinds of animals. Yeah. So this is the concept of semantic space. That means words with similar meanings are located closer to each other in a vector space. And here we have an example. For example, you can see that adjectives, nouns, and here what is adverb, they are clustering, to be closer to each other because they are similar kind of words. And also we can find that, for example, here, man and woman, king and queen, you can find that they are on the same direction, which is also pretty interesting. That means, maybe man minus women is similar to king minus queen. Yeah, Okay, so this is the concept of word embedding. Yeah. So how do word embedding train? Yeah, this is a good question. There are many specific algorithms to train word embeddings. For example, you can minimize. Yeah. For example, you have a lot of yeah, text text in the text in the word like books and articles, and you use these training materials you can train a word embedding to find the so to find the relation between words. For example, in most of the text, man is appeared with woman. Yeah, they have high possibility to appear together, and then you should train the word embedding to make the embeddings of the two words to be closer to each other. Yeah, this is the general idea. Yeah, we have a lot of algorithm to train a word model to train word embeddings. Yeah, and the next part is that how do we represent the order of word? Yeah. So now for each word we have a word embedding, which is a vector. Yeah. So how can we let transform model to enter if we have multiple words, the order of these words, like man bites dog rather than dog bite man. Yeah, you know that they are exactly the same three words, but the order is different and the meaning is totally different. Yeah. So maybe we can also think of some very naive ways to represent the order. The most simple way is to represent the order with index. So for example we have word man bites dog, which is 0, 1, 2. We assign a number to each word to represent the position of the word in the sequence. Yeah. However, this will lead to problems in when when it is processed by a neural network model. We have already mentioned that neural networks do not like large numbers. Yeah, if some very large numbers like 1,000 such things to appear as an input to a neural network, it can hardly process them. Yeah, and it will almost surely lead to numerical problems. Yeah. So we need to think of a way to avoid the increase of the of index when the sequence is very long. Yeah. So a better solution and a very clever solution will be to use a combination of sine and cosine functions. So here we use a simpler we use a simplified example. Mm, for your understanding. For example, here we simply use a vector of north 2. The first component is sine position with n, and the first is cosine position. Yeah, so so the benefit is that it is always between -1 and 1, and we can shift this vector by k. For example, here the k is the relative distance between words. For example, man bites dog. You can see that dog is two words after the word man. So yeah. So when transformer models learn the learn the relation between words, it is very important that for example, maybe a transformer model would like to would like to focus on what is the word after after first word, for example man, with maybe mm, with the distance of 2. So the distance of 2 is man and this number 2, and it is dot. So here k equals to 2, and we can shift these positional encodings by k, yeah, with a linear transformation. That means, yeah, yeah, mm, we simply multiply the vector with a matrix, yeah, and we can get the shifted, yeah, positional encodings. Yeah, this is good for neural network models because neural network models is very good at learning, yeah, linear transformations. Yeah, for example here, yeah, we also have a list of word embeddings and with long nerves, and then we assign each word embeddings with a positional embedding. Yeah, in such a way, yeah, we give both the word embeddings and positional embeddings to the transformer model, and it can understand both the word and the position of the word in the sequence. Yeah. Okay. So so that is how we represent the word and how we represent, yeah, the order of the word. So the next question is that, yeah, given the word embedding and positional embeddings of the sequence, yeah. For example, what is your name? Yeah. So how do we predict the next word, which is proper to be to follow, yeah, the previous sequence? Yeah, for example, here, what is your name? End of sequence, and the most proper proper word that to appear might be I. Yeah, because we need to answer this question, right? So so the general process is that the word and positional embeddings is processed by multiple layers of multiple attention layers, mm, one by one. Yeah, and this is proposed in a paper in how many? Yeah, 2017. Yeah, actually, it is just 9 years ago. Yeah, not so far away. So the name of the paper is "Attention is All You Need." Yeah, which is super famous. And here there's one of the papers that all artificial intelligence learners need to read. Mm, or actually, attention. The concept of attention is not mm, is not firstly proposed in this paper. Yeah, before this paper, attention mechanism is widely applied in mm, in neural models. However, this is the first paper that build a model mm, only by attention layer. That means all the components are attention layer, nearly or no other, yeah, layers. Yeah. Yeah, before this paper, yeah, attention layer is typically an add-on, yeah, to some sort of like, yeah, recursive neural networks such like LSTM, such like this. However, this paper, yeah, proposed that, yeah, we can use attention layer to do all the stuff. Yeah, we don't need other layers. Yeah. So let's see, yeah, how attention layer works. So I would like to give, before we enter the formal definition of how attention layer works, yeah, I would like to give a very intuitive, yeah, example about attention mechanism. Yeah, imagine that we have, yeah, x-axis, y-axis, yeah, and we have coordinates. So let's say, yeah, we are standing, yeah, as a, yeah, original point with a 0, 0, and then we are looking, yeah, at three objects, yeah, three fruits, yeah, apple, pear, banana. So they have they have three they have three coordinates. Yeah, so we are standing here and we look at the direction of pairs. Which means we do attention on the pairs most. But that does not mean that we do not care about apple and banana at all. So actually imagine that you are standing here and you are looking as a pair. Actually, you will surely also paid a sort of attention on apples and bananas because they are paired together. They are not far away. However, there would be some difference. Between the attention strengths. Of the three fruits. You must, if you look at this direction, you must do attention on pears most and do attention on other two fruits less. And here consider that we assign a one hot encoding to each of the fruit. And then let's see how we do the attention, how we compute the attention on and give a result on the attention result. So let's see. So the direction of attention here we call it a query. So like and the coordinates of the three fruits, we call it three keys. And then the value behind the fruit, the one hot encoded here, and we call it value. So we have query, key, and value. So let's see we how we model the attention mechanism that following this direction, we attention pairs most, and we pay a bit of attention on apples and bananas. So firstly, we will compute some score between the query and all the key values. So apple, pear, banana, we will compute a score for each of the key. With respect to how the direction of attention match the key. So a very simple way is to simply compute the similarity, like cosine similarity or some sort of other similarities between the direction and the coordinate. So for example here, we can compute the score between Q, attention direction, and the pair, which is -1, 1. And we compute the similarity between the two vectors. You can see that it is 1 because they are exactly the same, right? So the attention direction is exactly match the coordinate of pair. And we compute the score between the key and the banana. It is not exactly matched, but it is still close. So banana is 0, 1, and our attention direction is -1, 1. And we compute the similarity, which is 0.707. Like this. And then we would like to what we would like to output is the it's a combination of values that like but the combination is not it's not like all keys are equal. It is a weighted sum. So the most attention object will be assigned the highest score, and we add them together in a weighted way with respect to the value. So here you can see that we add the three values together, but they are of different they're of different weight. Like the pear has the highest weight, and the banana has the lowest weight. So and we have this result. So generally speaking, this is how attention mechanism works. So that is, yeah, we have a query, we have a key, we have a value, and we compute the similarities between queries and keys to get a score. And then we use the score to do a weighted sum of the values. Yeah. Mm. So now return back to our transformer model, which process natural languages like words and sentences. So the process is actually pretty similar. Mm. Given a sequence, yeah. Firstly, yeah, for each of the word, which is represented by its word embeddings and precision embeddings. Yeah. So firstly, so we will generate a query vector, a key vector, and a value vector. Yeah, for each of the word. That we have 4 words. So we have so for each of the word we generate three vector query key value. And how this is done? This is done by simply by a linear transformation. Yeah. Mm, so Qi equals to WQ multiples EI and SBQ. Yeah, like this. So there's a linear transformation. Yeah, and all these linear transformation are printable. So so for each attention layer, the most important thing they would like to know is the linear transformation between word and precision embeddings, or the input vectors of the attention layers and the query key value vectors. Yeah. So after the generation of query key and value vectors, what we do is just what we have mentioned in the previous slide. So we compute the match score between given a query, Q, we compute the match score between Q and all the key values. Yeah, we compute the score. Yeah, we have a lot of ways to compute the score. But generally speaking, it is by similarity. Yeah. So we compute the score, and then we use the score to make a weighted sum of values. Yeah, like here, we have the score, we have a weighted sum, and to add them together. Yeah. Mm, by the way, in practice, we need to do some sort of normalizations, on the score to avoid that they are too large that they can if the value is too large, it can be hardly processed, by the neural network models. So we will do some sort of normalizations, and additional transformations, in such a process. But generally speaking, it is a weight. The output is a weighted sum for each query vectors and for each input vectors. We have a unique query vectors, and we use the query vector to generate weighted sum, and we do some sort of additional transformation, and we get the output vectors. Yeah. For each input vectors, we get output vectors. In such a way, the format of input and the format of output of a attention layer is exactly the same. So in such a way, attention layers can be stacked, mm, layer by layer. Yeah. Mm, okay. Yeah. So imagine that. Yeah, we have a sequence of word and precision embeddings. We process the input by multiple attention layers one by one. and we get a final list of vectors. So how do we use the um, the generated the generated vectors, to predict the next word that to be appeared. Yeah. So generally speaking, we can simply do this by a fully connected layer, which means we simply multiply the last vector by a matrix, by a trainable matrix, or simply by a linear transformation, with activation function. The most simple layers in neural networks. In such a way, and after a softmax, we can generate the probability. We can generate a vector whose length is the number of words. And then we just regard each values as the probability of each word. And we can simply choose the word with the highest score as the final output. Like here, maybe assume that this 0.35 is correspond to the word I. And if this is the largest, if this is the largest, then we simply predict I as the output. Or we can treat it as a probability distribution and sample from the distribution, to get a more randomized yeah, output. So the last part is that it has some further readings. So actually, if you want to understand the process in more details, I would like to suggest the first article, the illustrated GPT-2, which has a very detailed introduction about how the attention mechanisms work in GPT-2. Yeah. Also, the following articles will also help for you to understand the mechanism behind transformers. So that's all for my presentation today.
Uh, Thank you, Shiha, for your time and the presentation. There's a one question. What skills and projects would you recommend for students who want to build a career in AIML, and how can they effectively transition from learning concepts to deploying production-ready AI systems?
Mm, Sorry, I ask me questions. I just
Yeah,
missed up.
there's a question. Uh,
Okay.
what skills and product, what skills and projects would you recommend for students who want to build a career in AIML, and how can they effectively transition from learning concepts to deploying production-ready AI systems?
So is this question listed on the chart,
No,
or I need
no,
to
no.
find it else?
Someone else in the registration form. I'll push in the chat.
Okay. So
Uh,
mm, okay.
I have pasted in the chat. You can scroll down.
So sorry. Mm,
You can scroll it down in the chat, and then you'll see
okay.
the question. Scroll down.
Okay. Oh,
Yeah.
yeah.
There.
Oh, what skills and project? Okay. I understand. Yeah. So mm, actually, to be, because in today's world, we know that the code agent is super powerful. So actually, so today, actually, I think if this question is asked in 2 years ago, I might have a very different answer. But today, yeah, the coding agent is super powerful. So, so I think students should avoid starting from vibe codings as the beginning. Yeah, so, so I would suggest them to, for example, write a very simple transformer model. And it can train it by themselves, yeah, on some simple data. Yeah, so I think it is pretty important, yeah, to understand the mechanism behind models, and this can be only achieved when you actually do it by yourself rather than prompting the coding agent to do so. Yeah. Yeah, you can surely prompt in the coding agent and they can give you a very satisfying result, um, but you do not learn a lot from this process. So I will still, yeah, suggest, yeah, students, yeah, to try to build models by themselves, yeah, program by themselves, and yeah, even their implementation might be much worse, yeah, compared with coding agent. But only in such a way you can understand, yeah, how the model runs, yeah, by yourself, yeah. So yeah, and how can we effectively, yeah, do transition from learning concept to deploying production-ready AI system? Uh, mm, actually, I think with the help of coding agent today, it is not so hard for students to deploy, yeah, uh, artificial intelligence models to be production ready. However, if you would like to gain experience, it is almost sure that you still need to do some sort of internships, yeah, in in AI companies or those companies that need to deploy AI system in real world. Yeah. I think that is the most efficient way. Yeah, do an internship in a company. Yeah. So what is the next question? So shall we follow the order of the order in the chat box, or maybe I will just follow the order of the chart box. So how the word embedding models trained. Yeah. So yeah. So I think I already answered in my presentation. Yeah, we have many ways, yeah, to train the word embedding, and the main concept is that if two words always appear in a same sequence, then you should make the distance, yeah, between the word embeddings between the two words, yeah, closer. Yeah, okay. And the semantic space is similar across models or different in models. Yeah, that depends. Yeah, but generally speaking, I think it is pretty similar across models. At least the idea, yeah, the idea is very similar. Mm, maybe in practice, yeah, they have some subtle difference, but the idea is very similar. You can always, yeah, you always believe that, yeah, in almost all word embedded models, the distance between like words cat and dogs are pretty close. Do we have to make clusters of English grammars and words relations before training on AI to guess the next word? Sometimes the word embeddings can be known directly, as training variables. In such a way, we do not to make we do not need to train word embeddings before we train the transformer models. But I think maybe if you but you know that word embeddings is appeared it appeared before the invention of transformers. So although today we may not we may not need to train a word embedding alone. Maybe we can directly treat it as trainable variables. But the concept of word embedding is still very helpful. Even it is trained directly in a transformer model, you can still you can still have the concept of semantic space, and you can still know that the word the similar word will have closer distance. Let's see. How much of your day is coding? Actually, that depends on whether you whether you take the coding agent into consideration. I think today, if you are working in industry, nearly all the people are using coding agent to do codings. So that is why I mentioned that for students, you may need to try to avoid relying on coding agent too much. But for me, firstly, at least on my work day, that means 5 days out of 7. I'm all doing coding, but most of the coding is done by coding agent. So the coding process, the coding done by me, is only a very small part. So what steps should we take to make a new transformer architecture? Secondly, how will we know that where changes are required in existing transformer when combining CNN and transformer to address both local and global features for segmentation problem? What steps should we take to make a new transformer architecture? I maybe I will rephrase the question like, how can we improve the transformer architecture on some maybe new task. So actually this is not easy. So if you can do some really innovative improvement on a transformer model, actually you can publish a good paper. Maybe I can share some of my experience on this because I proposed a new transformer architecture on generating logic circuits. So that is one of my main papers. So so generally speaking, firstly, you need to have a very good understanding of the transformer model, that's for sure. And then you might think of what is the problem in such an architecture, and how do we and what kind of techniques can help us to resolve the problems in the text that I pay attention to. Yeah, for example, yeah, what the text I concentrate to is the generation of logic circuit. Yeah, the generation of logic circuit is different from generating natural languages. That is, yeah, for natural language, actually, it is common, to it's common to have some blur. Yeah, that is the meaning is not exactly precise. Yeah, one sentence you may have different understanding of the sentence. However, for logic circuit, you need to be exactly precise. If you want to implement a logic circuit for a specific function, yeah, only a smallest a smallest difference would make the logic circuit wholly failed. So that means how can we develop a transformer model that can avoid any mistakes. Yeah, so we always generate the result that does not make any violations of the constraints. Yeah. So to solve these questions, actually, I found a technique very helpful, which is constraint programming. Yeah, you can Google on constraint programming, and this is a technique that constrain the generation during the during the output process to help you to make the output of the model to have specific format. So then I find that if we combine the two techniques together, actually we can have a way to constrain the generation of logic circuit to exactly match the functions that I would like to implement with a logic circuit. So so this is an example by myself. How can we make a new transformer architecture, or how can we improve the transformer architecture to satisfy specific needs? And secondly, how can we know that where changes are required in existing transformer when combining signage and transformer to extract both local? Actually, if you have a very specific features that you would like transformer to be improved, I think that maybe the best way might be to simply ask Gemini or some or some or ChatGPT, because they have this is another question about the innovation of of model improvement in today's research era. So you know that today's large language models are very capable of combining one concept with another concept and combine them together and solve a specific problem. Large language models are really good at this today. So for this question, I will simply suggest you to ask Gemini or ChatGPT. If I join data team and learn analysis and Power BI stuff here, how can I move toward AI in the future? Actually, it depends on what sort of AI you mention. If you would like to move toward like an AI company whose goal is to train and improve a large language model, I think you have a lot of things to do. At least you need to have a very good understanding at how today's large language model works. not only about transformers, but also about more advanced technique to train a good large language model that's capable to do more advanced tasks rather than just completing the sequence. Yeah. So such techniques might include RLHS, SFT, or RAG, or something like this. Yeah. Yeah, you can Google on such term these terms and also reinforcement learning. Yeah. So if you would like to join such kind of AI team, yeah, the competition is very high, and you need to have a very deep understanding on how this large language model works. Yeah. What tech should we choose in 2026? Would it be AI, ML, or still web dev, or on high demand, and what tech stack in your view? What other fields is highly emerging in future? Yeah. Yeah, it is a question that I have been questioned a lot, and also I am questioning myself about this. Yeah, what tech should we choose in 2000 and in 26 in today? So, so in my opinion, is that if you only try to do like web development or maybe front end or back end, something like this, it is pretty risky. I would like to say, because today's code agent is more and more powerful, and a lot of junior tasks for web development and front end, back end, can be replaced by code agent. So in my opinion, maybe some fields that are still pretty challenging and not so easy to be replaced might be the field that you need to you need to communicate with real people. So if you're only if you are only work on programming, without engaging with real people, I would like to say, it is risky that your field might some days be replaced by a coding agent one day. Yeah. So if you are mentoring a final year undergraduate who wants to become an AI ML engineer or researcher, what would your roadmap for the next 12 months look like? What would you prioritize? What would you avoid? And looking back, are there any decisions or missed opportunity you wish you could recognize earlier? Yeah. If I am mentoring a final year undergraduate, maybe my roadmap is that it depends on how the undergraduate student have it is good at the foundational knowledge of artificial intelligence or machine learning. If they already have a pretty good understanding of how artificial intelligence and machine learning works, maybe I would suggest him to work on a research project that and try to solve specific problems that has not been very properly treated in today's artificial intelligence. Actually, I have some sort of such problems which I can provide to undergraduate student, and I would let them try to solve these problems and try to find some sort of technique that is suitable to solve them. And and what would you avoid and looking, what would you avoid? Actually, what would paralyze and avoid? Actually, I would paralyze on the understanding of the student themselves, of the solutions they propose. They need to understand. So if they propose a solution to me, I need to make sure that they understand the solution themselves rather than even if the solution can perfectly solve the problem that I proposed. Because in today's world, it is very risky that that the solution is simply generated by AI. So this is what I would paralyze. And are there any decisions or missed opportunities you wish I would recognize earlier? Actually, there is surely some sort of opportunity I miss, but considering that we cannot predict the future, I can only make sure that I do the right decisions and I do the best decision at that time. So yeah. Mm, mm, for me, I do not think I missed a lot of opportunities or standing at today. I think at that time, it is sure that I cannot recognize. For example, today's coding agent is so powerful. That is what I cannot expect. Expect to. I can recognize earlier, but. If transformers are trained solely on predicting the next token, how can we structurally measure what they can actually develop in word models? Word model is another topic. So which is still compared to large language model, I think word model is still premature. So. Actually, I do not have a very good answer to this, but generally speaking, transform model seems to like it is only to predict the next token, but today's transform model is actually much more complex and really huge. Maybe in some sort of sense, we cannot treat it fully as a model that only predicts the next token, but so how can we structurally measure whether they're actually developing models? So academic era still debating on this. Some people believe that they can never develop a true word model, but some people are not. In my opinion, if you want to develop an actual word model, maybe the main obstacle is that you need to interact frequently with the actual word, and whose cost is very high. I don't think the architecture is the main barrier, but the high cost of interacting with the real world might be a severe problem.